Hello friends, in this video we will learn more about the concept of reciprocal lattice and we will try to plot the reciprocal lattice of a two-dimensional rectangular lattice. So in the previous video we already mentioned the importance of defining reciprocal lattice. It is very useful to study X-ray crystallography, lattice vibration, electronic band structure, etc. So in order to understand the crystal itself, it is important to know its reciprocal lattice because its behavior in many other aspects is defined by the reciprocal lattice. The reciprocal lattice actually represents the Fourier transform of the direct lattice. So we saw in the last video that the diffraction pattern we obtained from the direct lattice, from the real lattice, is actually the reciprocal lattice, correspond to the reciprocal lattice. So we can define that the reciprocal lattice is the Fourier transform of the real lattice. Now the atoms are arranged in real space and that is called direct lattice. So what you visualize as the distribution of atoms in space is called the real lattice or direct lattice. Suppose this is the distribution of atoms, then we will call this as real lattice. But reciprocal lattice is imaginary and it is constructed in the reciprocal space where the lengths are in inverse relation with the direct space. This space where we construct reciprocal lattice is also called momentum space or K space. So we construct reciprocal lattice in momentum space or K space. That is actually an imaginary space. The real atoms are arranged in real space. There we construct real lattice or direct lattice. So what you have visualized until now in your textbook are all real lattice or direct lattice. But when we come to study in detail about the crystal, it is important to define reciprocal lattice. So we have learned about many of the properties of reciprocal lattice. Let us try to plot or construct the reciprocal lattice. So let us learn the important steps in constructing the reciprocal lattice of a crystal. Now the first step is to consider a common origin to draw a from a common origin draw a normal to each crystal plane. So, draw normal to each plane from an origin, from an O. Then, the length of the vector that we draw should be equal to 2 pi by d. Set the length of these normals equal to 2 pi by d, where d is the interplanar spacing of the plane. Now the third step is to mark points at the end of these vectors. Mark points at the end. So let us see how it is done by choosing an example. So let us choose a rectangular lattice and let us construct its reciprocal lattice. So this is a rectangular lattice. Suppose the length in one dimension is greater than the other, so it is called rectangle. Suppose this vector is vector A bar and this vector is vector B bar. So surely vector A and vector B are perpendicular to each other. Now let us try to construct the reciprocal lattice of this crystal, this structure. So this is the direct lattice. These all dots, red dots, correspond to the atoms in the crystal. Now let us try to build the reciprocal lattice of this structure. Now I am going to choose an origin. Suppose this is our origin O. And what should we do? From the origin, we should draw normal to all the possible planes. Suppose this is a set of plane. You can see what is the distance between these planes? The distance between these planes is A. Now from the origin, I have to draw normal to these planes. So I am drawing a vector. This vector is normal to this set of planes. And what should be the length of that vector? The length of that vector should be 2 pi by interplanar spacing, which is A here. So I am choosing the length of this vector, green vector that I am drawing perpendicular to the set of these planes to be 2 pi by A. And then what should I do? I should plot a point at the end of this vector. Mark a point. Now in the next step, let us consider another set of plane. So you can see here, this is a set of plane, right? There are other planes above that. And what should we do? From this origin, we should draw a vector, and the length of the vector should be 2 pi by interplanar spacing, which is B here. So I am going to draw a vector. Its length is 2 pi by B. We know since B is less than A, 2 pi by B will be greater than 2 pi by A. So I should set the length of this vector, 2 pi by B length vector, should be greater than the first drawn vector. So I am constructing in that way. I am going to put a dot at the end of that vector. Similarly, let us consider other sets of planes. Here you can see another set of plane are there. You can construct planes in a diagonal manner like this. Here was an atom. And the next plane will be here. These are all diagonal planes. Another plane will come here and so on. Now what should I do? From the origin, I should draw a normal to these planes. The normal will be like this. And the length of the normal should be equal to 2 pi by interplanar spacing. You can see for these planes, the interplanar spacing is very low compared to A and B. So the length of this vector will be very much greater than all the vectors that you draw. This is the first vector that we constructed, and there is a point at its end. Then the second vector was much bigger than the first vector. Now the third vector is even bigger because the interplanar spacing is lesser for the new sets of plane. So its length is higher, and I should draw a point at its end. Similarly, let us draw other sets of planes. Here you can see another set of plane here. This is yet another plane. And from the origin, I am going to draw a perpendicular to this plane, and the length should be 2 pi by interplanar spacing. Here you can see the interplanar spacing that you measure here is exactly equal to the interplanar spacing that you measure here. A little difference that you notice is due to the problem that I made during drawing. But if you measure or use your logic, you can understand that these sets of planes are exactly like this set of plane. You can see the plane that we draw through here are same like this because these are rectangle. So again, I draw a vector from the origin perpendicular to these sets of planes, and I am going to put a dot at the end of this vector. The length of this vector is 2 pi by d. And similarly, let us consider other sets of plane. Here is a set of plane in the back side. Let us draw a perpendicular to that plane from the origin, and I am going to set the length of that vector to be equal to 2 pi by a, because a is the spacing in that dimension. So let us put a dot at the end of that vector. Similarly, we can construct other vectors. perpendicular to other planes. For this set of plane here, you can construct a vector like this, and its endpoint will be marked by a dot. So you can see this is the evolved reciprocal lattice. Here again you will get a dot, and again you can put dots here by considering other planes. So this is the evolved pattern that you get. This is the reciprocal lattice of this rectangular lattice. You will finally get dots here by considering other sets of planes like that. So the red dots correspond to the real lattice, and the blue dots, the blue pattern that we have drawn here, is the reciprocal lattice of this direct lattice. So the red is the real lattice where atoms are arranged. Red dots correspond to the positions of the atoms, and the blue dot correspond to the reciprocal lattice. It is actually drawn in the K space or the momentum space. And here you can see each dot actually correspond to a set of planes. Each dot will give you the interplanar spacing D and the orientation of the plane. From the origin, you have drawn perpendicular to each set of plane. So each dot from the reciprocal lattice will correspond to orientation of the plane as well as the interplanar spacing. The distance from the origin will give you the interplanar spacing of that plane. So this is a vital information that you will get from reciprocal lattice. So you can see we can actually construct the reciprocal lattice for different sets of lattice. Now we have constructed the reciprocal lattice of a rectangular lattice. If this is the real lattice, then the reciprocal lattice will also be rectangular. Here we have seen the red dots are in the rectangle shape, and the blue dots are again in rectangle shape, but its dimensions have changed. So this is how you construct reciprocal lattice. You can also construct reciprocal lattice in a similar manner for other different structures, other different two-dimensional structures. And if you look at the properties of these vectors, in the direct lattice, we will define two vectors as the primitive translation vectors, A bar and B bar. This is the A bar and this is B bar. What are primitive translation vectors? From one particular point to reach the next point, you have to travel that vector. A bar is the vector that separates two adjacent points. B bar is the vector that separates two adjacent points in the second dimension. So they are called primitive translation vectors. A bar and B bar. Similarly, we can define the primitive translation vectors for reciprocal lattice. They are defined as A star and B star. They have different values when compared to A bar and B bar. We can find that the primitive translation vectors of real lattice, which are A bar and B bar, and the reciprocal lattice, which are A star and B star, are related by some equation. We can find that A star dot A is equal to 2 pi. So this is the relation between primitive translation vectors of real lattice and reciprocal lattice. And B star dot B equal to 2 pi. But A star dot B and B star dot A, both these are 0. So these are the relation connecting primitive translation vectors of real lattice and reciprocal lattice in two dimension. We can also define a translation vector in reciprocal lattice. It is defined by G equal to N1 A star plus n2b star. I will give you a short video about the meaning of the translation vector. So as of now, let us learn that the translation vector is defined by n1 a star plus n2 b star. For a two-dimensional case, in the case of the two-dimensional picture that we see now, we can find that a star equal to 2 pi by a and b star equal to 2 pi by b. So this can be defined in the case of the reciprocal lattice that we saw now, the rectangular lattice. The common relation between reciprocal lattice vector and real lattice vector are given by these relations. So I hope you understood today's lesson. We just went through the meaning of reciprocal lattice, the real lattice, the reciprocal lattice. Then we learned to construct the steps to construct a reciprocal lattice. Using that step, we constructed a reciprocal lattice of a rectangular lattice, two-dimensional lattice. Then we also learned about the translation vectors in real lattice and reciprocal lattice and the relation between the translation vectors in reciprocal lattice and real lattice. I hope you understood today's lesson. Thank you.